Okay, so yesterday we talked about types of data and types of sampling, and we went over some of the things that are done to kind of make the samples not as accurate, to push the data in a certain direction with our samples. So today I want to look now at, once we have the information, what do we do with it? So we had two types of data that we talked about. We talked about categorical and numerical. So let's begin with categorical. Categorical data, again, was data where the answer to that question puts you into a category. You know, yes or no, or whatever other category there was, you know, favorite color, presidential candidate you're going to vote for, whatever. So to do categorical data, the first step, of course, we have to have a list of data. So I'm just going to make up a set. We're going to do favorite color here. And I'm going to say I'm only giving people the choice between red, green, and blue. So let's say we survey people and we get red, red, green, red. One, two, three, 4, 5, 6, 7, 8, 9, 10. So there's a set of 20 responses. Looking at that set, you might be able to think, you can just look at it and get a really good idea of what the most common response was, but you might be surprised. I mentioned yesterday a little bit of psychology involved in statistics and how certain colors, you know, stick out and draw your attention, and we'll look at a little bit more of that today. Psychologically speaking, cognitively speaking, the human brain is only able to take in between 7 and 13 things at a time. So when you're looking at this set of 20 items, 20 responses, you can't really look at it and take in the whole thing at once. So if you're focusing here, it might look to be very obvious that red is the most popular color. But if you shifted your focus and we're focusing here, blue might appear to be the most popular. If you're focusing on this end, green might make that distinction. So we need to organize it to make that decision, that observation, much more apparent, much easier to do. And the first way we do that is we arrange things in what we call a frequency table. So here we're listing colors, so we're going to make that our first column, and we're just going to list red, green, and blue. Then here we're going to list their frequency. How often does each occur? Now I left a little space here because I'm going to add kind of a working column into this. And my working column is going to be tally. I'm going to take this column out. If I were to make a finished table to present in a paper or a presentation, I would take that column out of there and not include it. But while I'm working, it makes it a lot easier to set it up. So I'm just going to tally out. So I've got red and red, green, red, blue, green, blue, red, blue, green. Just crossing them off as I tally them. Well, there's red, blue, red, red, blue, blue, green, blue, green, green. So what we see here is we get final tallies of 7 red, 6 green, and 7 blue. Now when you're looking at that list of responses, very few people would think that they are that close to being the same. Like I said, depending on where you're focused, especially at the beginning here, it looks very apparent that red is way more than any others, but it's not. They're very, very close to the same. Now for a few data values like this, you know, only 3 possible responses, it's not too bad to look at the table to decide which one was the most popular and which one was the least popular. You can very quickly see green is the least popular, slightly least popular here. But if I gave you a bigger spectrum of colors, maybe 7 or 8 choices, it would be a little more difficult to do. So the table gives those exact values broken down, but the next step will be to display it graphically, graphing it. One possible graph would be a bar graph. And I'm assuming you guys have all seen a bar graph. You can do a bar graph either vertically or horizontally. I'll start out with a vertical orientation here. So a vertical bar graph. I know it's kind of ironic that I'm using blue to list the colors red, green, and blue, but we'll make do with it. We put our categories across the bottom here. Then we're going to put a scale up the side. 7's our largest number, so we have to make sure we go up to at least 7. Then we'll put in our bars. Red was 7. Green was 6. And blue was 7. Now, one thing I was very careful to do when I was making this bar graph, and I didn't do a great job of it, but I was trying to make the bars the same width for each bar. One thing that is done, one thing that is done to try to trick people with a bar graph is something like this. So red is 7. Green is 6. Blue is 7. Now looking at this, even though it's not hard to see that the top of the bars are the same for both red and blue, that red bar is thicker. It's fatter, and because it's wider, psychologically your brain latches onto it as being bigger. Even though it's the height that matters here, that your brain is saying, oh, red looks bigger. So at first glance, that's what you're drawn to. Now here, because the numbers are relatively small, it's not difficult to see what the value should be. But that is one of the weaknesses of a graph. The strength of the graph is you can quickly look and see, hey, green smallest. These two appear to be approximately the same, if not exactly the same, and they're the largest, the most common. Let's say we're comparing 3 companies here. And I'm going to compare companies A, B, and C. And so we have company A, goes out like that. Company B, and C. Looking at this bar graph, your first instinct, of course, it is really easy to see that B is the tallest and A appears to be the shortest. But your first instinct might be that company, if we're looking at sales here in thousands, it might be easy to think that company B has twice the sales as company A. But if you look closely, you'll see that this is 250,000, this is 300,000. Company A has just under 270,000. Company B has a little bit more than 290,000. So it's not a huge difference. But what's been done here is this little break in the axis. So we're not starting at 0, we're starting at a larger number. Now that is good in one way, as it allows us to see the differences more clearly, but bad in another way, that it is showing, it gives you that initial response that B is twice as big. It actually blows up those differences and makes them look bigger than they actually are. If we had graphed this without that break in the scale, oops, helps if I make this even here. There we go. A would go about little under 270, somewhere in here. B would go 290, somewhere in there. And C, about 280. So even here you can see, and I purposely spaced them to make it a little harder to see, but you can see still that A is the smallest and B is the largest. But they look very, very close to the same. And this is a more accurate, more, I don't know, honest. I don't want to say honest because that's not necessarily true, but a better depiction of their total sales, where this one highlights the differences. It's something to be careful of because this is used a lot to try to, this break in the axis is used to try to fool you into thinking that differences are bigger than they are. Now, as I was starting to mention, you look at here, though, this one, even over here, you can't tell exactly what A is. I mean, you can tell it's just below 270,000, but the exact number is impossible to get from this graph. So the graph is good for comparing bigger or smaller and getting an approximate value, but not exact. If you wanted the exact value, you would go back to a table like this one. Okay, so I'm going to reconstruct my table here for just a second. Another way of graphically displaying categorical data is a pie or a circle graph. To do a pie graph, we're looking at what's called relative frequency or percent frequency. For that, I must start out, apologize for my messiness there, I must start out by finding the total frequency. If I add those all up, I get 20. So now my relative frequency is found by taking the frequency for that value divided by the total. So 7 divided by 20 is 0.35. 6 divided by 20 is 0.3. And 7 divided by 20 again is still 0.35. So that's a relative frequency. Those numbers should all add up to 1.00. Now they might be a little off. It might be 1.01 or 0.99 because rounding off to a certain decimal place. The percent frequency, just slightly different, would be 0.35 is 35%. 0.3 is 30%, and 0.25 is 35%. And again, those should add up to really, really close to 100%. In a perfect world, they'd be 100%, but round-offs might throw those off just a little bit again. It's the percent frequency that we want. We could use the relative frequency because most of us are pretty good at converting decimals into percents really quickly. But it's the percent frequency that we really want for the pie graph. So for our pie chart, making a circle. Now, if this were 20 years ago or more, we'd take 360 degrees in a whole circle, and we'd find 35% of that and take out our protractor and mark out that many degrees. For now, we don't need to be that precise. We're going to use just benchmarks. We know that half of a circle is 50%. We know that a quarter of a circle, had I divided this up evenly, is 25%. So if we cut that in half, that's 12.5%. And we could cut it down to make 6% if we wanted to. 6.25%, and so on. So what we're looking for here is things that are close to one of those. Well, 30% is 25 plus 5. So we could do 25% here. I'm going to do it in black. Well, that's 25% here, plus a little bit less than the 6. So like that. That's 30%. That's going to be my green. 35% is 25 plus 10. So 10 is not quite 12. So a little bit less than half of the 25. That's going to be red. And the rest of this, of course, will be blue. I'm going to get rid of those auxiliary lines in there just to clean up my graph a little bit. Still a little bit of a mess in there, but you guys can see there's my circle graph. Now these percents were all close to the same, so it's really tough to distinguish a difference. But you get the point. That's close enough for what we're going to do. If you wanted to do an exact circle graph, you could pull up Excel and you could do it really quickly. I don't know how much experience you guys have in Excel, but I'll just show you quick. Helps if I can spell. I can do a circle chart, circle graph, pie graph. Just like that. And there it is. Done out to perfect scale. The way we want it. All ready to go. Now if I wanted to put it more detailed, of course we can format data series and do all sorts of stuff to it. Yeah, I'm not going to get into editing it here, but you guys get the point. Okay, so we don't need to be perfect with that. Let's look now at numerical data and how we organize numerical data. We have numerical data. There's two types. We talked about discrete. And discrete, remember, was counting. Like how many cars are owned in your household. And the frequency table for that is going to look almost exactly like the categorical frequency table. So 0, 1, 2, 3, 4. Let's say that nobody in our survey had more than 4 cars owned in their household. You might have 7 people surveyed own 0 cars, 32 that own 1, 24 that own 2. Let's see, what is that? 63. 11 that own 3 and 1 that owns 4. And there you have your frequency table. And again, this will be pulling out of data, doing the tally column, but I'm just throwing the data in there because you've seen that process. And graphing, you could do a bar graph with this, very similar to the bar graph you would do for categorical, or a circle chart, finding the percents and all of that. What I want to spend more time on is looking at grouped or continuous numerical data. If I have continuous data, an example might be height. Let's say we're measuring the height of several people. And let's just list out some heights here. Let's see, we're measuring to the nearest tenth of an inch. So someone who's 68.4 inches. I'm not going to the 50s. Let's go 62.3, 71.8, 73.2, 67.9, 69.1, 70.1, 64.7, 65.1, 68.9, 72.3, 63.4, 68.2, 73.1, and we're down here, 65.9. So that's only 15 listed out there. But even there, it would be impossible to list out, wouldn't be impossible, it would be very unuseful to list out each individual value, because I don't think any of these are repeated more than once. They'd all have a frequency of 1. That wouldn't tell us a whole lot. So what we do is we make up classes or groups. So we're going to group these. And in our frequency table, we're going to divide them up into groups that are equal size. That's the first thing. And that have no gaps in between them. So we have to have equal size and no gaps. So what this is measured down to the 1/10 of an inch, so I can't have a gap bigger than a 1/10 of an inch. Let's see, 62 looks to be our smallest, so let's do this. We'll do 62 through 64.9, 65 through 67.9, 68 through 70.9, and 71 through 73.9. You'll notice here, each of these is the exact same size. It goes up by 3, 3, and 3. If I subtracted these, I'd get 2.9 for every one of them. So they're all exactly the same size. You'll also notice there's no way, measuring to the 1/10 of an inch, there's no way that anything could fit between 64.9 and 65. No way anything could fit between 67.9 and 68. And it can't be that we just don't have any data values in that range. It has to be that there's no possible measurement measured to that precision that could fit between them. Now for frequency, I'm just going to count here 62 to 64. Let's see, there's 1, 2, 3, looks like 3. 65 to 67, 1, 2, 3. 68 to 70, 1, 2, 3, 4. And 71 to 73.9, 1, 2, 3. Oops, I missed one there. 4. There's 5 actually here for this one. The 70.1 should have gone in there. So there it is. There's our distribution. That should add up to 15, I hope, if I counted correctly. And we have our data grouped together. Now we can see that for the ranges there, 68 to 79 is the most common range for basically a 3-inch range. Gives you a little bit of a picture of the data. Now for graphs for this, they're similar to our graphs for the discrete data. But instead of a bar graph, we make something called a histogram. A histogram is always vertical, never horizontal. And we're going to list on the bottom here, we're going to list our groups or classes. Like this. Those are groups, and then their frequencies. So I got a list of scale up here. 1, 2, 3, 4, 5 is my highest. You're going to notice something a little bit different about how I make these bars. So for 62 to 64.9 was 3. 65 to 67.9 was 3. 68 to 70 was 5. And 71 is 4. You'll notice the bars here are made tight together, which is done for a very specific reason. When we look back up here at our bar graphs, there's space between the bars because there's really no logical connection between these categories. In fact, there's not even a logical order. I mean, I could put green first and it wouldn't make any difference. So there's no logical order, no flow from one category to another. So there's no connection. So we leave space between them. A little bit of that psychology of statistics again. We're putting space in there to represent the psychological space between them. Down here, however, not only is there a logical order, I mean 62 comes before 65, but 64.9 flows right into 65. So they flow together, so they're tight together to demonstrate that flow. Also, kind of like we did with dot plots, or we'll talk about more with dot plots, you can draw a curve through the center of the top of those bars to kind of represent a data distribution or an approximate data distribution. If we were looking at plotting individual values, by the way, a data distribution, we mentioned this briefly, test scores. So let's say we had a test where people scored between 70 and 100 on their test. And by the way, I messed up my scale there quite a bit, but that's okay. Let's say the first score was an 84. We put a dot above the 84. 89, 76, 92, 86, another 89, another 84, and 81. Now, if we only have a few scores, we don't get much off of this plot. But if we have a lot of students taking, or a lot of people taking this test, the plot fills in. The dots start to stack up. And what we get is a little bit of a picture of how this data looks. And this is what we call distribution. If those dots stack up and we draw a line that kind of goes through basically the top dot on each, above each number, we get a distribution or curve. The height of the curve here, you can see, tells us how many dots were below it at that number, or how many items had that value. So the height of the curve is a value. Same type of thing can be done with the group data, even though it's going in groups instead of individual values. And that's called the distribution. And we're going to talk a lot about that coming up next week. There's one more type. All the data we've done so far is kind of a snapshot of what we're looking at. It's a single moment in time. What we want is called a cross section. You're looking across maybe several items at a single moment in time. You know, companies A, B, and C, or 3 different colors. What we're going to look at now, this final little piece of data to display, is called time series data. In time series data, we're looking at a single value just over several periods of time. You might track tuition costs. Per credit. I'm just going to use WITC's approximate numbers here. So let's go 2000. We're going to go every couple of years here, so I'll go 2002, 2004, 2006, 2008, 2010, and we'll stop at 2012. Generally in education, things go on a biennial, 2 years at a time. So anyway, let's do our scale up the side here. There's $100. So each of these marks is $20. In 2000, tuition was just below $100 a credit. 2002, it went just above. 2004, actually went down about $1. 2006, it went up a little bit. 2008, it made a big jump. Oops, make sure I stay above my number there. And 2010, small decrease. 2012, small increase. So we can connect our dots here. And what this shows us is changes over time. Now, by the way, a lot of people are tempted to do this. Don't do that. That's meaningless. At year 0, there was no value. It wasn't $0. So anyway, on this graph, we can see a few things. One is we can see where is it increasing. Well, how do we know if it's increasing? Well, the slope is going up. So it's increasing here, 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 and here. We can also tell where is it increasing the fastest. Because it's the steepest right here. So that's where it's increasing the fastest. We can also quickly identify where is it decreasing. Where was the price falling? Well, here and here, both of them slight, but this one's where it was decreasing the fastest, or the most, for that 2-year period of time. So just by looking at the slope, you can tell a lot. You can also figure out at what year was it the most expensive. Well, 2012 is the highest point on the graph. That's when it was the most expensive. What year was it the cheapest? 2000 slightly lower than 2004, so 2000 is when it was the cheapest. So those are the strengths of graphs, is comparing, finding the largest, finding the smallest, comparing two values. Was it more expensive in 2006 or 2010? Well, 2010 is higher than 2006, so it was more expensive in 2010. For finding exact values, using a table is much more convenient for us. If I had a table, right here you cannot tell what was the price per credit in 2002. Well, you can see it's just over $100, but you cannot tell the exact price. So for exact prices, tables do not work well. So now our next step, now that we've summarized data graphically, which is the tables and the graphs, our next step is going to be to summarize data numerically. And summarizing data numerically goes off of that concept that we talked about of a data distribution. If you put those dots down there, you get this curve. And it's what we call the bell curve, or technical term for it is the normal curve. And most distributions in nature naturally take on this bell-shaped curve. If you ever heard of something called a norm reference test or a normalized test, any of you have done the state of Wisconsin testing, that's what that is a norm reference test. It's all based on a bell curve. The scores of all the students who take that test form very, very close to a bell curve or a normal curve. And if you think of that number line being down here representing the values, the value that is below the center of that curve, that's the value that had the most items that took on that value. And if you're talking about a test, the most students who had that particular score, because it's under the highest point of the curve. You get out here, students who had this score, well, the curve's lower there, so there's very few students who scored really high, and very few students who scored really low. Well, if we're looking at this curve, there are two things we can do to summarize it, to distinguish it from other curves. I'm going to draw another curve here that is identical to it, except that it's moved to the right. Looking at these curves, we would say that they have a different center. The center for the black curve is there. The center for the blue curve is up there. So the center has moved. Even though the rest of the curve is identical, they have different centers. This curve has the same center as our black curve, approximately at least, if my artwork were better. But it's different because it's narrower. The black curve's much wider. So that is what we call the spread or the dispersion. How spread out is the data? How big is the range of that data? How far apart are the numbers within that data set? And if we have those two descriptors, we get a very good picture of the data. And there's actually a lot we can do with that data. Starting on Monday, we're going to look at some small data sets and start doing those calculations. For now, I think Swamigan, you guys are going to have to go soon. So the pages in the book that correspond to this are 321, 1 through 7, the odds, just looking at graphs. Page 326 through 330, 1 through 10, and finally page 339 through 340, there again just 1 through 9, the odd. So not a lot to do there. Most of you have, I'm sure, have seen the graphing and stuff like that. Maybe the frequency tables are a little new, but hopefully not too big of a stress for you. Next week, as I said, we're going to talk about summarizing numerically with measures of center and spread and possibly measures of position. And then we're going to talk about what what do those measures tell us about our data? What can we figure out from that data? And then probably by Friday, we'll do a little bit of a basic probability discussion. And that following Monday is our last unit test already. So you guys have a great weekend.